Molecular orbital theory deals with the establishment of molecular orbitals, and we establish molecular orbitals, molecular orbital wave functions via one combination, and that combination is called LCAO combination, linear combination of atomic orbitals. With the help of that LCAO principle, we can establish a set of molecular orbitals. Let us apply LCAO principle for new molecule, fluorine molecule. Once we get the molecular orbitals, once we arrange them in the proper energy sequence, we can distribute the electrons in them by applying Boole principle, Hertz law of maximum multiplicity, and Pauli's exclusion principle. And that electronic configuration will give us the idea to describe bond order, means number of bonds, and magnetism of the molecule. Let us see the application.
Let us understand the formation of F2 molecule through molecular orbital theory. We need to establish various molecular orbitals. We should understand their energetic. Then we have to distribute the electrons in those molecular orbitals. Electronic configuration of fluorine is 1s2, 2s2, 2p5. If I talk from the lowest energy orbital, that's a 1s orbital, it is considerably inner orbital. Just imagine two fluorine atoms are coming closer. Then which portion will be overlapped? Outer orbitals will undergo overlap. Inner orbital will not experience overlap. If I talk in terms of energy point of view, actually energy of 1s orbital of one fluorine and energy of 1s orbital of other fluorine is same. So they should form molecular orbital as per first condition. Second condition, symmetry also is same. They should form molecular orbitals. And third condition, appreciable overlap should be there. There is no proper appreciable overlap. Therefore, those 1s orbitals will remain non-bonding. Overlap integral is 0 because there is no interaction. Those will remain towards each nucleus only. So each fluorine nucleus will be with this 1s orbital and electrons. Let us consider the labeling for this 1s as K because it is a first shell. Next energy level orbital is a 2s orbital. 2s orbital of one fluorine will interact with 2s orbital of other fluorine because both have the same energy. Are they of same symmetry? Yes. What is the kind of symmetry? Sigma. Why? Because if I rotate that 2s orbital around the internuclear z-axis, then there will be no change in the phase, so it is symmetric about internuclear z-axis or cylindrical axis, principal axis. Therefore, symmetry is sigma. So sigma symmetry is there for both orbitals, so they should form molecular orbitals. There is appreciable overlap. So two atomic orbitals are combining, two molecular orbitals will be the result. One bonding, we say it as sigma 2s, which is a result of constructive interference, which is a result of addition of wave function. Energy decreases. And other orbital, sigma star 2s, which is a result of destructive interference, subtraction of wave function. Energy increases relative to respective atomic 2s orbitals. Entry of electron in sigma 2s will help for bonding, and entry of electron in sigma star 2s will oppose for bonding. If equal number of electrons are there in bonding and antibonding, assistance and opposition will be to equal extent. So net result will be 0. Let us come to the higher energy orbital, 2p orbitals. 3 2p orbitals are there. Triplet is there on each fluorine, 2px, 2py and 2pz. Understand their orientation. We are considering 2pz orbital, lobes are left right. 2px orbital, lobes are towards us, away from us. 2py orbital, lobes are up and down. And one lobe, if is positive, opposite lobe will be with negative sign. Let us find symmetry of 2px orbital. If I rotate 2px orbital around internuclear axis, then the lobe away from us will come towards us. So positive lobe will become negative, negative will become positive. It means change in the wave function is there, change in the wave phase is there. So it is not symmetric about internuclear axis, z-axis, principal axis, cylindrical axis. So what is the type of symmetry? Pi. Similarly, 2py orbital also is of pi symmetry. What about 2pz orbital? Suppose right side lobe is positive, left side lobe is negative, and if I rotate that 2pz orbital around the internuclear axis, bond axis, then right side lobe will remain to right side, left side will remain to left side, positive lobe will remain positive, negative will remain negative. There is a no change in the wave function. There is a no change in the wave phase. It means this orbital is cylindrically symmetrical. It means this orbital is of which symmetry? Sigma symmetry. Same kind of triplet is there on the other oxygen atom. So when two oxygen atoms will come closer, at that time, which orbitals will interact first? Px, Py or Pz? Means which orbitals will interact strongly? Px, Py or Pz? Of course, Pz. Because they are approaching directly to each other. Head-on head interaction, axial interaction, and to this we have given the name sigma interaction. It is because of symmetry. Strongly if they are interacting, then resultant molecular orbitals also will show decrease and increase strongly. Means bonding sigma to pz orbital will decrease to more extent, and anti-bonding sigma to pz orbital, means sigma star to pz orbital, will increase to more extent. Means I have to talk about all molecular orbitals from 2p sublevel. Sigma to pz should be of low energy. Yes, it is of low energy, but it was not the case in case of low atomic number bearing diatomic molecules, means maybe lithium, beryllium, boron, carbon, nitrogen. Here, systematic as usual, expected MO diagram is there. Reason is energy gap between the 2s and 2p. Fluorine being with large number of the protons, the good strong nuclear attraction is experienced by electrons, and gap between 2s and 2p increases, and because of increase in the gap, usual energy level diagram we are finding. The true reason is interaction between the molecular orbitals, and to make this concept clear, you can go through other video, separate video titled Making Sense for MO diagram of nitrogen molecule, N2 molecule. So 2pz and 2pz will interact to produce sigma 2pz and sigma star 2pz, lowest and highest, that we discuss. What about other two orbitals? They also will interact simultaneously, but kind of interaction, way of interaction, amount of interaction is different. There's a lateral interaction, there's a lateral overlap, side-side overlap. It is a weak overlap. So resultant orbitals will be pi to px, pi to py, which are the bonding orbitals. And extent of overlap experienced by x orbital and y orbital is same, so their energy is same. Which word we use for the same energy orbitals? Degenerate. Similarly, antibonding orbitals produced by 2px and 2py orbitals with respective overlap are pi star to px and pi star to py. Their energies are also same. The energy with which bonding pi orbital decreases, with that much amount of energy, antibonding pi orbital increases. This weak interaction, what we am seeing, that we say generally pi interaction. Why? Because symmetry of the combining orbitals is pi. That's the main point of labeling those bonding or labeling those interactions. So in molecular orbitals resulted due to interaction between 2p orbitals, sigma to pz is of lower energy, then pi to px and pi to py both have the same energy, then pi star to px and pi star to py both have the same energy, and last sigma star to pz, it is the highest energy orbital. What do you think? Can 2px orbital of one fluorine interact with 2p orbital of other? Because both have the same symmetry. No, they can't form the molecular orbitals because appropriate, sufficient, proper overlap will not be there between them. Just imagine one up down orbital is there and one orbital towards us and away from us. When they will come closer, then there will not be appreciable overlap, because in between who is coming? Z orbitals are coming. So between them proper interaction will not be there. But where lobes are larger, so laterally they can overlap. So px can overlap, py can overlap. But though symmetry of px and py is same, they will not overlap in this molecule. In case if they would have been overlapping, we need to consider the respective molecular orbitals. But reality is not. But that is not the reality. Therefore, we are not considering their interaction. Otherwise, one need not to blindly accept only 2px and 2px and interact, 2py and 2py will interact. Symmetry is a one different aspect. So for that, I am suggesting go through the other video making sense for MO diagram for nitrogen molecule. Now, once we know the various molecular orbitals, let us see the distribution of electrons in those molecular orbitals. Lowest orbitals are non-bonding orbitals. Lowest energy orbitals are non-bonding orbitals, and we are labeling them as K and K. 4 electrons are over in those. Total I need to distribute 9 plus 9, 18 electrons. Remaining 14 electrons, how will we distribute? 2 electrons in sigma 2s, 2 electrons in sigma star 2s. So 4 electrons are over. Left 10 electrons. 2 electrons will enter in sigma 2pz. So how many electrons are over now? 10 electrons are over. 11th electron will enter in pi 2px. 12th in pi 2py. 13th will pair in pi 2px. 14th will pair in pi 2py. 15th will choose higher orbital pi star 2px. 16th will enter in pi star 2py. 17th will pair. 18th will pair in pi star 2py. So we are following Boole principle, Hertz law of maximum multiplicity, and Pauli's exclusion principle. Yes, all 18 electrons are over. So from this electronic configuration, can we find the bond order? What is the formula to find bond order? Bond order is equal to number of electrons in bonding orbitals minus number of electrons in antibonding orbitals divided by 2. See how many electrons are there in bonding orbitals? 2 in sigma 2s, 6 in sigma 2pz, pi 2px and pi 2py. So 8 electrons are there in bonding orbitals. How many are there in antibonding molecular orbitals? 2 in sigma star 2s and 4 in pi star 2px, pi star 2py. So 6 electrons are there in antibonding molecular orbitals. So 8 minus 6 divided by 2, answer is 1. There is only one bond in fluorine molecule. Let us describe this one bond because of which kind of interaction it is. If I talk about sigma 2s, yes, it can help to form one bond, but sigma star 2s cancel that efforts. So there is a no net result. Sigma 2pz, 2 electrons are there. Sigma star 2pz, no electron. Yes. So sigma 2pz, 2 electrons can form one bond. Which kind of bond? Sigma bond. Let us talk about pi orbitals. Pi 2px and pi 2py have 4 electrons. Means they should form 2 pi bonds. But antibonding pi star 2px and pi star 2py, they have 4 electrons. So those will oppose to formation of those 2 bonds. So pi bonding will not be there. So whatever one bond we calculated, that is sigma bond. How many unpaired electrons are there? 0. So what will be its magnetic property? Diamagnetic. Let us understand distribution of electron representation for fluorine molecule. Representation is F2. 3 lines means equivalence, and in special bracket all molecular orbitals are represented, especially by green and blue coloration. Non-bonding orbitals are represented. Those are not polycentric but are part of the molecule. 2 electrons are there in each orbital, that's each cell, and the label for that shell is K. K from one fluorine, K from other fluorine, KK. Total 4 electrons are there. Remaining molecular orbitals are represented by white color. Electrons in bonding orbitals I represent by white color, and in antibonding orbitals I represented by yellow coloration. Sigma 2s orbital 2 electrons, sigma star 2s 2 electrons, pi 2px and pi 2py. They are degenerate, therefore is equal to sign is there. Their energies are same. Each orbital has 2 electrons. Sigma 2pz 2 electrons. Pi star 2px and pi star 2py, they are degenerate, is equal to sign is there. Pay proper attention. 2 electrons are there in each antibonding pi star orbital, and last sigma star 2pz has no electrons, and afterwards our special bracket completes. As a homework, usual question for you: mention bond order and magnetic property of diatomic fluorine. Bond order means one number will be there. Magnetic property means whether it is paramagnetic or diamagnetic. That only you have to mention in comment box. Be regular in replying the questions.
Application of molecular orbital theory to the fluorine molecule is clear to you. Let us compare the result of valence bond theory and molecular orbital theory. As per valence bond theory, as the electronic configuration of fluorine is 1s2, 2s2, 2p5, one unpaired electron is present on one fluorine atom. Similarly, other fluorine atom has a one unpaired electron, and those unpaired electron will pair to form one single bond between fluorine and fluorine. Yes, molecular orbital theory also said that. But which kind of bond is there in the fluorine molecule? That wise explanation is given by the molecular orbital theory. As per valence bond theory, because of pairing of electron, or since there is no any unpaired electron available, molecule should be diamagnetic in nature. And molecular orbital theory also says yes, Fluorine molecule is diamagnetic. So though the results by the molecular orbital theory and valence bond theory are the same, but molecular orbital theory is always dominating over the valence bond theory. I am not saying valence bond theory is perfectly wrong. There are the applications of the valence bond theory. Let us study the molecular orbital theory for next molecule, that's a neon molecule, in next part.